Welcome to the Sophistic online documentation. In this video of the composite bridge tutorial, we show how to calculate shear forces for the design of the shear connection between structural steel and concrete. According to Eurocode, these shear forces should be calculated using the properties of the uncracked section, even in areas where the concrete acts in tension. For this purpose, we provide the option to calculate the shear forces using the uncracked section properties. To do this, please open the task and select the corresponding calculations. In general, the design of the shear connection has to be done for the ultimate and also for the serviceability limit state, here using the characteristic combination. Therefore, we provide the calculation of shear forces for both cases. Let's go to the corresponding tab and select for the ultimate limit state and serviceability limit state calculation the load cases superposed for minimum and maximum shear force we set, which for the present structural system will give the maximum axial shear force for the design of the headstart anchors. For one of the ultimate limit state load cases, here for example load case 3025, we also request a detailed output with extensive output depth, and we want to have it at the right side of the inner support to check the calculation of the shear forces. After running the task, we can take a look at the report. For each of the calculated load cases, we get a table showing for each section along the design element the calculated shear forces in each shear connector. Here we have only one. And we get a plot showing the distribution of the shear forces along the girder. Let's check in the detailed output how the shear forces are calculated. In the plots that we have requested, we can see on the right how the shear forces in kilonewton per meters develop through the construction history and after adding the live loads. On the left, we can also see the corresponding axial stresses in the section. The forces in the shear connection are highlighted in green. You can see that they start to develop after the hardening of the concrete slab. From the axial stress plot, you can also see that the concrete slab has tensile stresses. Contrary to the previous calculations, it is considered as uncracked in the stress calculation. Remember also that we have reduced the elastic modulus of the concrete for the sections around the inner support. To account in the analysis for the reduced stiffness due to cracking. Note that for this task of calculating the shear forces for the shear connection, the original elastic modulus of the concrete type, in this case round about 34,000 Newton per square millimeter, is used to get the uncracked cross-section properties in the whole girder. We have also the same behavior for the shear forces in the serviceability limit state. For the actual design of the headstart anchors, you can now, for example, copy and paste the shear flows to an Excel sheet. Please note that the shear forces are calculated on cross-sectional level purely from the shear forces and the torsional moments in the section. Local effects, like the effects of concentrated axial forces applied to the section, or effects from sudden changes in the cross-section, like for example depicted in figure 6.12 of Eurocode 4, are not considered and have to be treated by the user separately. Okay, that's it about the shear forces for the design of the shear connection. In the next video, we will show how to calculate stress ranges for the fatigue design checks.